Separation techniques. First one here, let's talk about separation techniques are used to separate mixtures. Mixtures, of course, can be homogenous or heterogeneous, okay, where it's either uniform or not uniform, and something is dissolved in something else and you can't see the individual particles under the homogeneous. And then hetero, you have the ones where you can see the individual particles. Because substances in a mixture are physically combined, that's the key word there, they're physically combined. That means we should be able to separate them into their individual pure substances based on their own physical properties. Okay? Now, there are different methods. We have filtration. We have evaporation. Chromatography, which we're going to do a lab on, I believe, next week. Decantation. Magnetic separation. And distillation. So these are going to be our 6 different ways that we are going to separate mixtures and get our components of the mixtures away from one another. Now, filtration uses a porous barrier like the filter paper to separate substances based on particle size. So if it's too big to go through the filter paper, it collects on the filter paper, just like in our lab. The purple precipitate you saw on the filter paper, and then what went through into the flask was just clear liquid. Works because tiny dissolved particles are too small to be filtered, but the non-dissolved solid particles are too big to go through. This is kind of common sense, and use the filter paper, you like fold it in half, and then you fold it in quarters, and then you kind of make it this cone shape to put into the funnel. And then you just set it up here and you have your nice funnel, and you put the stuff here. In this particular case, the little blue specks up here will get caught by the filter paper, and then the rest will go through. One main application, one that we see all the time and lots of people do themselves at home, is brewing coffee. Brewing coffee, of course, is you're filtering, and the large particles stay behind in the coffee filter, and then the other stuff goes through. All right, evaporation. Liquid from a solution evaporates, leaving behind the solid. Can be done quickly by gently heating the left out, dry up slowly. And what you'll see as if you gently heat it, the water will go away, and then whatever solid crystals will be left behind. And it will remain as crystalline residue. So all you have to do is heat it. You can do it in a beaker, evaporating dish, a couple other different things in order to recover the solid. Chromatography, like I said, we're going to do a separate lab on this, where we're using separate components of a mixture based on the tendency of each component to travel or be drawn across the surface of another material. You have a mobile phase and a stationary phase. The stationary phase is the paper. The solvent at the bottom is going to be the mobile phase because it's going to creep up the paper. It's going to go up the paper. And basically what we're looking at here, the speed by which the components move up the paper depends on its adhesion to the substance. So if it is more adhesive to the liquid or the solvent, it will go up further. If it's got more adhesion or similar to the paper, it will not travel up as far. Okay, and there's a little video here that we can watch. But as you can see, that one's like separating dyes. That's an actual like paper from the lab up there in the picture. Decantation, you're familiar with it because you did it over here in our lab. Basically, you pour off the top. You can do it with like the two liquids if they layer out like our mineral oil and our water did. Or if you have a solid at the bottom, you can pour off the liquid. That works. You can also use something called a separatory funnel in this picture, where it creates the layers for you, and then you just turn it, and you can drain it to that layer, so you're separating out the layers there. Couple of different things for decantation. Magnetic separation, obviously, in order to separate something by the magnetic property, is it has to be attracted to the magnet. Many metals are, some are not. This example is showing you solid sulfur and iron filings. The iron, of course, would be attracted to the magnet, whereas the sulfur would not, and you'd be able to separate it out. The distillation process, and I think I'm going to set this up for you to see when we do the chromatography lab. It's quite a complex type setup where you have like two flasks, one right here that's being heated, one that you're going to deposit the other liquid in. Now what you can do here is separate it based off of boiling points, okay? All right, so homogeneous mixture can be separated by distillation based on differences in the boiling points, okay? The one with the lower boiling point is going to go up first. It's going to come down this big tube called the condenser. And you have water running outside the outside tube of the condenser, which is going to cool it down. When it cools it down, it turns it back into a liquid to come out the other end in the flask. So I'll just have this one set up. You can actually see it happen in our lab. Here, if you wanted to separate out, and this is what they do for desalinization, when they need to separate the seawater, because there are areas that don't have a whole lot of fresh water. Basically what they do is they heat up the water, and this is not very cost efficient for energy, but you can separate it from the salt by heating up the water goes down the tube, and the salt would be left behind in the original flask. If needed, that's one way of doing it. Or if you're separating, alcohols from the water to liquids, same thing. Alcohol's boiling points are lower than water, so it would go up first and come out the other end. So this example, you would see at the very end, the salt would be left behind in this flask, and the pure water would be down there, coming out the other end. After it turned into a gas, then through the condenser here, it turns back into a liquid and comes out the other end.